So first and foremost, let me set the stage for, thank you. Let me set the stage for Kalman filtering. So what is Kalman filter? And what I want to talk about is why is Kalman filter needed? So let me set the stage. And I want you to kind of try to understand the logic. Imagine what you have is you are walking here and you see a person of interest, which could be your friend or someone who owes you money. So you see that person of interest. And this person is also walking. Now, assuming you have eyesight 20/20 and you can see that far, you know exactly where that person is going. So basically, you know that where that person is going. And you can adjust your speed and direction. In other words, you can change your dynamics based on where the person is. So here is what you're doing. You're observing the person and you are changing the speed or the direction. So please try to understand what essentially when you change the speed is thinking, you can think about it like you are tuning your gain. And when you are tuning your gain, the gain tuning is done using this observation. And sometimes your observations are perfect, that you know exactly where that person is. And that means you can tune your system very accurately because you trust your observations. And basically, you can change your gain accurately. Now, imagine you're supposed you are actually wearing glasses. You wear glasses, but that day you are not wearing glasses. So clearly, your observations will not be very clear. So maybe what you may think that this person is somewhere over here. You may see that there is a shadow, there is an image somewhere in between. So your observations are going to be imperfect. Still, what you want to do is you want to adjust your dynamics based on these imperfect observations. Do you agree with me? That is exactly what Kalman filtering is doing. Basically, what it does, it sees the ambiguity in observations, and based on how ambiguous the observations are, the filter would tune the dynamics. What I want to tell you is, think about it. You're walking through fog and all of a sudden you see a person and you see that person very clearly for a minute. So you know, yeah, that person is right there. And then you actually adjust your heading in that direction. After some time, all fog, you don't see anything. You see sort of maybe a blob somewhere. And then you know, yeah, I think that could be the person, but I don't trust that measurement as accurately as my previous measurement. So I'm going to walk in the direction that I'm continuing, but maybe I slightly change. So this slightly change, that intuition that we have, is taken care by Kalman filtering. So what it means is you kind of decide to trust the observation, or you can decide to trust the measurement, or you can trust the previous solution that you computed. So many a times something like this, like, oh, I saw that person in that direction, I started walking. Now I see some image, maybe that person is there, but still I'm going to continue follow my path because I don't trust the observation good enough to change my course. This is exactly what is Kalman filter doing. Only thing, the Kalman filtering dynamical equations provide the mathematical framework for adjusting or tuning these parameters. Now, at this point, I want you to imagine yourself in this situation. And I want you to answer two fundamental questions. First, when would you trust the observation? When would you trust the observation? And when would you trust your estimate, the previous estimate? One thing for sure, if so here is what I'm going to do. I'm going to look at the observation, and then if in my next step I reach that observation, which means my course correction was perfect. You agree with me? So for example, I saw some person there, I walked in that direction, and guess that person was there. So whatever changes that I made to my course based on that observation, they were correct. In other words, there was a very good correlation between the measurements. So what you have is, if whatever you do is validated with your assumption, then you basically trust what you assume. Once again, initially Kalman filter starts with certain assumption. Assumption here is I'm trusting my measurement. If your assumption comes out to be true, then that means whatever you did was trustworthy. So basically the Kalman filter gain kind of codifies this intuitive logic that we have when we use in our actual daily life. So basically we do this all the time, but Kalman filter gives a very theoretical framework to do this. And in today's class, I'm going to talk about more like the physics of the problem. And in the next class, we will deep dive into the hardcore mathematical equations. And again, it's a trivial task to apply Kalman filter for a 1 degree of freedom system, because finally the answer from 1 degree of freedom system is the same whether you do a low pass filter. But I would actually like to do a Kalman filtering on a simple measurement. And then I will show you how you can extend that Kalman filter for a multiple measurement system. And believe it or not, Kalman filter is implemented inside the teeny tiny drone that you have. So what we are doing is we are observing the system. And understand, this observation is not static. You are not observing just one time. You are observing it continuously. So this is dynamic observation. So Kalman filtering is deeply rooted in the theory of dynamic, or basically the dynamic observer theory. And what I want to do is I want to develop this theory from scratch, and then actually we will look at how to implement it. And then finally, I would show you how to code it and how to solve practical problems with Kalman filtering. So everyone understands that what I have here is the state space model. So what do I mean by state space? You have x dot on one side, you have system dynamics ax, and everyone is comfortable with this equation. X dot is equal to a times x. So if I have a spring mass damper system, my states are displacement and velocity, and I write that into state space equation. Next term here is the external forcing term. So for an example, if I have a spring mass system, mx double dot plus kx is equal to 0, this system can be written as x dot d by dt is equal to 0, 1 minus k by m 0 x and x dot. So I got my A. This is my A. This is my X. Now, if my spring mass system, instead of being zero on the right hand side, if it has an external forcing, say sine t, then this B comes in the picture. So basically, what is this B? B is 0, 1, and sine t is my U. Everyone understood this? So I have this system, x dot is equal to AX plus BU. A is a constant coefficient matrix. It can have time varying or varying coefficients, but for the matter in discussion, for Kalman filter to work, matrix A has to have numbers. You can't have sine t, cosine t, tan t, that type of terms in A. If you want to deal with that, there's an extended Kalman filter. So you have x dot is equal to AX plus BU. This is the perfect system dynamics, which means you know the system, you know the mass, you know the spring, you know that this is a second order system. And then what you have is you have y is equal to Cx. Now this is the observation, which means imagine you have this spring mass system, and here is the displacement scale. And what you are doing is you are measuring the displacement. So if you are measuring the displacement of the mass, this matrix C is going to be, and I want you to understand this, 1, 0, x dot. Are you with me? So if you multiply first row, first column, I get y, which is the observation, is equal to x. Everyone understood this? Now, if I'm measuring x and x dot at the same time, if I'm measuring x and x dot, so I'm measuring displacement, and imagine that I have a speed gun. I have a speed gun, and this speed gun is measuring the velocity. Then this matrix, instead of just one vector, becomes 1, 0, 0, 1. X dot, and my y is going to be 2 rows, 1 column. Do you agree with me? 2 rows, 1 column. Because check this out here. First row, first column gives me x. Second row, first column gives me x dot. So now my spring mass system, I'm measuring the displacement, and I have a speed gun, I'm measuring the velocity. You agree with me? I can reconstruct the velocity from the displacement, which means the first measurement, what I'm getting, can be used to derive the velocity, or I can come up with a device that is measuring summation of displacement and velocity. That sounds crazy, but think about it. Like if I have a device that is measuring summation of spring displacement and velocity, that is going to be something like this. Are you with me so far? So your observation can be anything. Observation doesn't have to be actual physical quantity. You are observing any state, square of the state, addition of the state, whatever it is. So basically, y is something that you are observing. Everyone understood this? So this is how the whole thing starts. Now, what I want you to understand is, for a minute, think about, like, the only thing that I'm sure about in this entire expression is the magnitude of the spring and the magnitude of the mass. So the only thing that I'm sure of is the magnitude of spring and magnitude of the mass, and I'm sure about the external forcings. The only thing that I know is mx double dot plus kx is equal to sine t is the equation. But I'm not very confident about the observation, because there might be some errors in this sensor. So there could be some type of errors. there could be some type of errors. There could be the sensor may not be precise. It may skip steps. There could be quantization errors. Sometimes the sensors are noisy. So rather than getting the clean signal, you get the jerky signal. So then what I have is I do not have X, but X hat. So what that means is I do not have X, which is the states, but I have estimates of the states. Are you with me so far? So the idea is, I want you to kind of understand what is happening. My equation is x dot is equal to ax plus bu. My observation is y is equal to cx. Observation is an algebraic equation. It's not a differential equation. The equation y is equal to cx. There is no dot or double dot. It's just an algebraic equation. 1 plus 2 is equal to 3 or something like that. Now, but problem with this is I'm not very sure that I'm getting correct observations. So what I'm going to say is whatever I'm getting, whatever I'm observing, they are nothing but estimates. So in other words, I'm not getting y. I am getting, for the sake of discussion, y hat. Okay. If I had 20/20 vision, I get y. But since I don't have 20/20 vision, I get some fuzzy number, and that number is y hat. But what I want to do is, I want to find out like how much total error is present between the system dynamics that I'm observing and the actual system dynamics. And I want you to pay attention here. So I want you to observe this guy is the difference between y times y hat. Do you agree with me? Because my y hat is c times x hat. And then this x hat will get propagated. And when I say propagated, what does that mean? I want you to think about it like you're not performing numerical integration on a variable that is sort of fixed, but there is some sort of variability in that variable. So which means all your integration, all your system dynamics now will be on x hat. And you are going to have an error. Clearly, this estimated dynamics, I'm going to call this estimated dynamic equation. This estimated dynamic equation is not same as your original equation. What that means is I really want to know what is the difference between the original system dynamics and the system dynamics that I'm actually observing. Are you with me so far? The whole thing started because I don't have perfect senses. I don't have 20/20 vision. I see the things blurry. That's why I need some type of estimate. But even though I'm seeing things blurry, I would like to know how much off I am. So to understand that, what I need to do is I need to take the original dynamics and subtract the estimated dynamics. So I need to take the original dynamics and I need to subtract the estimated dynamics. So this is my original dynamics, equation 1. And this is my estimated dynamics. Do you agree with me? Now, if you subtract, clearly A is going to remain the same. So I'm going to have x dot minus x hat A x minus x hat. As you can see, there is no change in BU. So basically BU in equation 2. So I'm going to say equation 2 minus equation 1. Equation 2 minus equation 1. Minus, what I want to do is, I'm going to have this equation, which is, please understand, L, Y is nothing but, please note, Cx minus Cx hat. Are you with me so far? Now, what that means is this equation becomes x dot minus a x minus x hat minus, can you see C can come outside? L C x minus x hat. Do you agree with me? Yeah. Oh, yeah. So, equation 1 minus equation, ideally, how do I, actually equation 2 minus equation 1. My bad. My bad. So actually, so let me see. The equation estimated value is x minus x dot. Yeah, equation 1 minus equation 2. Equation 1 minus equation 2. Did I do it right? X dot is equal to x, x minus x dot, cx minus x. Okay. So what I want you to think is, L is, think about it like a multiplication number, a factor. So what I have is, I have an error in the observation. And what I want to do is, and actually I need to explain this a little bit. Give me a second. So I have an exact dynamics. I have an approximate dynamics. And I'm assuming that the difference between the exact dynamics and approximate dynamics is sort of linearly related to the difference in my observations. So what I have is, I have my exact dynamics, x dot is equal to ax plus bu. My approximate dynamics is x hat dot is equal to ax plus bu. But what I'm assuming is the difference between these two, it's, again, that is an assumption. Could be true, could be false. It's somewhat related to the difference in the observation. And why this comes, there's a physical interpretation for this, why this comes. And this physical explanation is super important. So, because what caused the error? The error came into existence because I was not able to measure things perfectly. Which means whatever was the measure in the whatever was the error in the measurement, that has affected my dynamics. So that is L. So I'm saying that error is somehow affecting the dynamics of the system, and basically to correct that error, I'm adding that term over here. So that is called as the correction term due to sensor readings. Everyone understood this? L at this point, L is arbitrary. We don't know the value of L. Now what happens is, at the end, when you perform this subtraction, and I want you to understand this very fundamentally, because the thing that comes out of it is very, very nice. So what happens here is, you have an equation for something like x tilde dot, I'm going to call this x tilde. This guy is x tilde. This guy is x tilde, and x tilde is different than x hat. Okay, x tilde dot is equal to a minus L C x tilde. Are you with me so far? Yeah. Correct. But unfortunately, our Kalman filter is a linear filter. So that is the assumption we are going with. This is Kalman filter is a linear filter. As soon as the things become non-linear, Kalman filter does not work and you go to the extended Kalman filter. And many a times even extended Kalman filter doesn't work. So you have to come up with your own iterations of Kalman filter. And that is where GNC engineers make a lot of money. So to understand, okay, so right now everything is linear. We will talk about non-linearity after some time. Once we master linearity, then we talk about non-linearity. Now, what has happened is right now, I got an equation x tilde dot is equal to a minus L C x tilde. You agree with me? Now, at this point, I want to ask you a very important question. What is x tilde? What is x tilde? Really? What do we operate in PID? Error. So basically, x tilde essentially is the error. Do you agree with me? So what it means is now I have an error dynamics equation. And I want you to understand it's very fundamentally because sometimes you can just use PID to do what Kalman filtering is doing. So right now I have an error dynamics equation E dot is equal to 1 matrix times E. When would that error go to 0? When would that error go to 0? Very good. When would that error go to 0? I have an error dynamics equation x dot is equal to a minus LC multiplied by x tilde, wherein A comes from the system dynamics, that is known. C comes from the observation matrix, that is known, right? When is it 0? This error would go to 0. This error would go to 0 when the eigenvalues of this matrix are in the left half side of the plane. Are you with me so far? And what term will control the eigenvalues of this whole thing? L. Which means I can change the value of L. L is just a number. I can change the value of L so that as time goes on, this error goes to 0. What that means, and this has a very profound effect on signal processing analysis, is by choosing appropriate L, even though my observations are imperfect, I can get the accurate measurement, or I can get, my estimates would be very close to the true value. Everyone understood this? You can do same magic with PID, and I have a student who actually did that. But at the end of the day, I want you to understand what is happening is we are thinking in terms of just like PID, but basically the error is going to 0. What exact term I need to modify in the dynamics? So what I need to do is, here is what I need to do. I'm going to take a measurement, and this is where the crux of observation comes. I'm going to take a measurement. I'm going to feed that measurement into my system dynamics equation. And what I'm going to do is I'm going to add a correction term. And what is that correction term? The correction term is nothing but the difference between the true measurement and the actual measurement multiplied by the value of L. The problem here though is I do not know where truth is, but I know for the fact that I can choose appropriate value of L, and I can make this matrix negative definite. In other words, eigenvalues of this matrix are on the left hand side of the plane, S plane. And once it's on the my left, your right. So on the left hand side of the S plane. And what that means, even though initially my error, there will be some error, but as time goes on, finally my error would die down and I would get reasonably true love. Does it make sense? So I can't measure true value, just like I can't get true love, but I can get reasonably true values. So reasonably true value. So that is the beauty of Kalman filtering. Now, everyone absolutely clear about the dynamic observer theory? Okay. Now, next thing what I want to talk about is, wouldn't it be beautiful, okay, that rather than a fixed value of L, I change the value of L in every iteration? Wouldn't that be beautiful if instead of being used fixed value of L, I iterate value of L depending upon whether I'm how reasonably happy or not happy, that type of stuff. Okay. Here, something else I want to talk to you about, and sometimes people don't understand. Have you taken any class in the reinforcement learning, or are you taking any class? No? Okay. So what I'm going to describe here is something similar to the reward punishment. Here, basically, there is no punishment. There is only reward. Yes, there is punishment, but not as severe as in the reinforcement learning. So here, what we are discussing, the prediction corrector scheme that we are talking about, is similar to the reinforcement learning structure. In other words, I'm going to make a bold statement here. Kalman filter is a very crude form, or a very skeleton form of reinforcement learning, where the gains are tuned basically based on the reward and penalty. So here is what is going to happen, and I'm going to give you not the mathematics of it, but most importantly, physics of it. So please understand clearly, I can't randomly make corrections. Before making corrections, I need to predict. If my predictions come true, only then I would make correction. Do you agree with me? So I want you to think. So now you will see plus and minus. Has anyone studied? Did you study Kalman filter before? No. Yeah.
The nano degree last semester.
Oh yeah. Oh yeah. Nano degree. Okay. Now after my discussion, that you can tell me whether this explanation is good or nano degree explanation is good. I know you are not telling me this explanation is good, but that's okay.
Wait a
Yeah, write that in my evaluation. Anyway, so basically understand, I need to have prediction. As soon as my prediction are correct, prediction become correct, I can make changes. So what that means is I'm gonna have basically, here's gonna have, I would have three instances. One is prediction, one is actual, and one is correction. So, and I'm gonna do a little bit of jumping back and forth, tap dancing. I'm gonna do this to make sure that everything is working out the way it's supposed to be. So what's gonna happen is, first I have this equation, which is this. Please understand, this is not an x tilde equation. This is x hat equation. So this is an equation of the estimated dynamics. We do not have true dynamics. We don't have nothing true. So it's an estimated dynamics equation. X hat dot is equal to ax plus bu. And now what happens is we get an output. Okay, we get a result. And what I'm going to do is, I'm going to have a result. I'm going to correct that result using and L, which is time varying, multiplied by the difference between the previous observation and the current observation. So what I want you to understand is, everyone understood that logic for equation 2? I have an approximate dynamical equation. Why am I calling that approximate? Because please understand, in real life, you don't have MATLAB. Real life, you are getting data. And what we are doing is we are performing integration or running sum on the data. So basically, as we get new data, we continue to perform running sum. So I have this equation 2, but now what I'm going to do is I'm going to dynamically change value of L based on how much I trust the measurement. So basically, that same equation, I have x plus value, which is nothing but the x minus value. So this is the x value, x hat. I have this value. What I'm going to do is I'm going to correct this value. And my hope is, after I perform the correction, that this new value, which is x plus, x hat plus, is equal to the x hat value. Are you with me? So we are dealing with three things here. X hat is the estimated value. But in order to do the correct estimation, you need to do prediction and correction so that you get to the right estimation. At the end, we do not have true value. We are only dealing with estimates. And depending upon your algorithm, you can get the estimates that are super close to the true value. For nonlinear systems, now what you have is, if you have an equation which involves nonlinearity, instead of propagating the linear equation, which is x dot is equal to ax plus bu, I would propagate the nonlinear equation. And at the end, this logic remains the same. Predict, correct, and hopefully that correction is very close to the estimation. Everyone understood this? This is the crux of Kalman filter. Now comes how it actually operates. And to be honest with you, I haven't really talked about the math. So I'm going to talk about the math in detail because I want you to be absolutely clear about Kalman filtering. So basically, when you go to an interview, I guarantee you, if you go to a robotics company, if you are going to go to Google, or if you go there, a roboticist, system engineer, software engineer, Kalman filtering question typically is asked in one of the technical interviews. In 7 or 8 technical interviews that you go through, somebody somewhere will ask about particle filter, Kalman filter, extended Kalman filter, or how would you fuse sensors, and that type of. You had a question? You have a question?
Curious about what you did with the dynamics with BU.
Dynamic view that got cancelled.
Okay.
So finally, what I'm doing is I'm subtracting 1 minus 2, right? So BU goes away. So this is how it works. Now what happens is, clearly, I have a true value. Can you see that true value I'm showing? So basically, this is the true value. We don't have access to this true value. Nothing in this world is true. So basically, except my love for teaching. So basically, as you can see, that x is the true value. Now what I have is I have some measurements. I'm getting x plus s, and I'm getting some measurements at the instance which are x minus s. So what I want you to think about, at time is equal to t2, what I have is I have a predicted value x hat minus. What does x hat minus means? It is the value of x at time t is equal to 2, that is predicted by the algorithm. This predicted value is clearly not close to the true value. Do you agree with me? But I'm going to add a correction term. I'm going to add a correction term and pull that value down, and that basically goes to x plus. So what happens is, if I were to perform this prediction correction continuously, then I'm reasonably accurate. I'm going to follow that path. Yeah.
How do we know the correction value is down? I mean, will we already know the value of X? That's how we put the correction value down.
Depending upon what you believe. I mean, I'm not. So basically, if you think your measurement, what you get is the right measurement, then you would weigh your measurement more. If you don't trust your measurement good enough, you will trust your current estimate. Once again, going through the fog, all of a sudden, fog disappears, and I can clearly see you, and I walk towards your direction. After some time, it all becomes foggy, and I saw an image somewhere here, but I do not trust if that is the right direction. So what I'm going to do is, depending upon how clear your image is, I would kind of change my course somewhere in between. So depending upon whether I trust my measurement or whether I trust my estimate, the direction correction flips back and forth.
Is it for the same time instance?
It's for the same time instant, but at the same time instant, you have three values: previous, predicted, corrected, and sort of estimated. And your hope is that your corrected value is very close to the estimated or true value.
Is this x cap plus
Hmm?
x cap plus
Mhm,
22?
mhm.
Did that come out of next reading?
Yes, it actually comes up. First, you measure x minus, and that is actually important question. And for that, actually, I need to work out actually I had to work out a simple Kalman filter, and I would do it in next class. So at the end, what you are getting is you are getting x hat minus. X hat minus is corrected using, please understand, what is y of Tn is the current observation minus, so Cx hat is the value you actually got, and the multiplied by a value of L that actually tells you how much you trust the new value that you got. And this won't be, I have to actually solve a Kalman filter by hand, then only you will understand, because you can run how much, you can see the code for Kalman filtering. MATLAB has excellent toolbox. You can run it and you will see that converging. But what happens is, imagine you have a voltmeter, okay, and that voltmeter is going to give you fluctuating readings. And at the end, you really want to know what is the true value. That true value you can never find out, but you want to find out an estimate that is reasonably true. So what you do is you perform Kalman filtering on the series of values that you are getting. So finally, your Kalman estimate is very close to the true value. The only issue is people do not do that for a simple varying signal, because the low pass filtering would yield the exact same result. That's why people. So if I tell you that you have a signal that is changing with respect to time, perform the Kalman filtering and tell me the value, somebody would say that is stupid, because I can just do a low pass filtering, get rid of the noise, or just find the running average, and then that would be the value. So at the end, what's going to happen is, if you have a one-dimensional signal, 1D signal, Kalman filtering approaches low pass filtering or mean average filter or weighted filter for one-dimensional signal. Power of Kalman filter is not in simple filtering. Power of Kalman filter is in sensor fusion. What is the sensor fusion? Like you are getting observed. So now I want to set this problem up as a sensor fusion problem. So imagine you have an IMU and you have a GPS. IMU is noisy, so the error, integration error goes on increasing. GPS is accurate, but it's very slow. So which means every so often, 1 second or 2 seconds, you are gonna get a value which is supposed to be super duper accurate. So what are you gonna do? You are going to find out the difference between the value that you receive from GPS and the value that you calculated, and then find the difference. And if that difference is too big, then you say, hey, I'm way out of error. The other way of doing it, I take that error, multiply by a suitable gain, and add it to my current measurement, and that is how I correct it. Everyone understood this? So this is how the Kalman filter works. And if you look at the Kalman filtering predictor corrector structure, you receive measurements at time. And now I want you to understand that you have an IMU data. You have that IMU data you don't trust because it's drifting. You are getting GPS data and you are using this Kalman gain sort of L to find the error, multiply that error by that L, and then add that to your current measurement. And if you do it correctly, you will notice that after some time, even though your measurements are not very accurate, you would get reasonably good estimates. Is this understood? So Kalman filter is actually the process wherein what it does is now you are estimating the quality, whether your estimate quality is good or your measurement quality is good. Now, I want to emphasize this here. For example, you get GPS signal, you get GPS data. How do you know that GPS data is good or bad? For that, there is something called as dilution of precision, DOP. You have HDOP, horizontal dilution of precision, and you have VDOP, vertical dilution of precision. If that number is small, which means your GPS measurement is more accurate. So depending upon the dilution of precision, you can decide whether you trust the GPS more or whether you trust your IMU more. So what happens is you start receiving the measurement, and depending upon quality of the estimate or quality of the measurement, you kind of blend them together. Does it make sense? So that's exactly how it works. Now, the next part is going to go into the math of Kalman filtering. And to understand the math of Kalman filtering, we have to actually talk about something called as the quadratic forms. And I'm not gonna discuss the math today because I would let you a little bit digest and reflect upon what we discussed in today's class. So, but I'll tell you what is coming next. So now we will kind of go into developing the mathematical machinery that enables us to use Kalman filter. So you would have the quadratic norm, quadratic form, which is again sort of a matrix pencil. And if you think about it, is like what you have is you can take a look at Wikipedia and see what do we mean by quadratic forms. And basically quadratic form is nothing but a Lyapunov function or a matrix where it's a positive definite matrix. The next thing we are going to talk about is multivariate Gaussian, which means you are getting 2 or more measurements, but those measurements are imprecise and they vary in a Gaussian fashion, which means they are distributed around mean and the distribution is dictated by the variance. The idea is what happens when you have 2 or more Gaussian measurements. So for an example, think about it like you are trying to measure the distance, but the thing that you are measuring is moving and the thing where you are on is also moving. Right now you have 2 variables. So basically the measurement is moving and where you are, the reference where you are taking measurement from is also moving. So you got these 2 distributions. What is the effect of that combined error on the overall distribution of error. So we have something called as the multivariate Gaussian, wherein you have two processes and both of them are normal variations. But how do you combine these two together? So basically for that you get multivariate Gaussian. Then what happens is with this tool, with these two tools, we are able to derive the dynamics equation for the Kalman filtering, wherein you have the dynamics x dot is equal to ax plus bu. Now, the thing that you see here is the system dynamics also is imprecise. So in the previous case, we talked about x dot is equal to ax plus bu. That was the system dynamics equation. But you now have eta, and that is basically the stochasticity or randomness in that dynamics. So basically, you get sort of random variation in the dynamics. You don't mean, and again, it's not deterministic, it's not constant, it's changing, it's random. The only thing you know about that randomness is that randomness follows the Gaussian pattern. Everyone understood this? And next part is you have something called as that eta is called as the process noise, and then you got mu, which is the measurement noise. So which means now you are dealing with two noise sources, one the noise in the process and noise in the measurement. I'm going to discuss this in very much detail, step by step, but I want you to understand what happens. And now you have something called as the measurement covariance. Now what is the meaning of covariance? Covariance means whether two or more quantities moving in the same direction or in opposite direction or in random direction. So for example, so if you study hard, you get good grades, which means that is heavily correlated. If I study hard, I get good grades. So that is an indicate, that is sort of the covariance. So you can find out the covariance between one quantity or two quantities or more quantities. You can find out the cross covariance, which means what happens if one quantity increases, other quantity increases or decreases, that type of stuff. And the process covariance Q is basically the uncertainties that are present in the system that are clubbed in the process covariance. And these R and Q matrices, they help us tune the Kalman gain in real time. Now, okay, I'm just gonna give you an outline of the derivation, but I will derive these equations again and I will solve an example. So what you do is you first start with a prediction. Basically, you predict what next is going to be. You perform the correction, and then you find the error in the estimation, and then you find the covariance of estimation error. Now, I want you to understand this covariance of estimation error. That is an important quantity. What that means is whether my estimates came true or they came false. So that is the covariance of estimation. And then what you have is you have some type of an estimation objective. And with that estimation objective, what you do is basically in between measurements, you can perform prediction, and using the estimates, you can actually find out if you actually either numerically integrate. So this equation, what you see here is continuous time Kalman filter. We generally don't use it. We always use the discrete time Kalman filter. So what you see here is you see the integration, convolution integral and integration, but usually the Kalman filter is basically a simple difference equation. Entire Kalman filtering code can be written only in 4 lines. but math behind Kalman filter is more than 4 pages. So then you perform the integration, and then between the predictions, what you do is you find the error estimates, and then at the end, what you do is you solve the error estimate equations, and then use those error estimates for the correction, and you can go through the math. So you are propagating the prediction values, you are propagating the measurement, you are measuring the corrections, and at the end, what you do is you perform the measurement, prediction, and correction. And lastly, you do the covariance update. Perform covariance update. Clearly, you need to do approximations. And finally, once you have done this, you get this equations, and you write 4 lines of MATLAB code that will do all this. So math is long, and to be honest with you, to use Kalman filter, you don't need to understand math. But the problem here is very rarely, I mean, Kalman filter will use in 60-70% of the cases. But in the remaining cases, you won't be able to use Kalman filter because your processes will not be Gaussian. Your system is not going to be linear. For Kalman filter to work, the process noise and measurement noise has to be Gaussian. For classic Kalman filter to work, your system dynamics has to be linear. And most of the system dynamics is either nonlinear, and most of the process noise and sensor noise is not Gaussian. So again, as I showed you, that math is intense, and it can be made more intense if you use stochastic calculus. But what I'm going to do is I'm going to use a step-by-step approach, and I will give you the alternate form of this long derivation, and I will derive that in next class, and I will work out a problem. Ito calculus, Ito calculus. So yeah, but so yeah, it's a new to me too. Ito, yeah. So the calculus that we are studying is Riemann calculus. Okay, what do we mean by Riemann calculus? Riemann calculus means integration of x dot is equal to x. Yeah, do you agree with me? Or derivative of x is equal to x dot. When things are random, you just can't take derivative and you can't take integration, because clearly random quantities, they change randomly, they are not continuous in between. So you cannot interpolate in between two samples because they jump. So all the bets are off. The regular Riemann calculus does not work, and for that you have to learn something called as the Ito calculus. What does there is something called as the fractional calculus. What is fractional calculus? Fractional calculus is, remember dx by dt. Imagine you have dx hat by dt hat. That is fractional calculus. You use that in control theory. Because what happens is there are some cases where if you use fractional calculus, the very super complex problem become very easy. So it's like you change your glasses and use different tools. It's like you can't use a flat screwdriver to open a Phillips screw, right? If you want to open a Phillips screw, you need a Phillips screwdriver. That's why. If you are solving the problems which are suitable for Ito calculus, use Ito calculus. For problems where you use fractional, you need fractional calculus, use fractional. Imagine you have a fractional differential equation, then what? You can't use your regular calculus to solve a fractional differential equation. So use fractional calculus. And with that, did I tell you Redkar's uncertainty principle anytime? So if you want to study fractional calculus is extremely useful when you want to study Redkar's uncertainty principle. What that means is you know where red car is. You know what red car is doing, but you do not know where red car is and what red car is doing at the same time. Yeah, for that you need fractional calculus. I'll stop here. Okay, I'll see you next class and have a good weekend, everyone.